Hello everyone. In this video, we would like to discuss elements of theory of dynamic networks. In particular, we will talk about the challenge of computing in a highly dynamic environment and the recent research in this area. In previous years, computing technique could be considered as statistic and predictable. In contrast, dynamic network is a network that changes with time. Nowadays, we are rapidly approaching the era of dynamicity and of the highly unpredictable. Why do researchers and scientists pay more and more attention to dynamic networks? First of all, a great variety of modern network systems are highly dynamic both in space and time. Secondly, theory will continue sitting at the center of progress in our science and its necessity toward our understanding of dynamic networks. Thirdly, many traditional approaches and measures for static networks are not adequate for dynamic networks. Lastly, we still do not really know how to compute in highly dynamic environments. According to some latest reports, the number of mobile-only Internet users has already exceeded the number of desktop-only Internet users. More than 75% of all digital consumers are now using both desktop and mobile platforms to access the Internet. The theoretical and analytic approach, which prominent in computer science research from very beginning, has been invaluable in modeling real-world systems and problems. However, we have reached a point at which a large gap has been formed between existing systems and applications on one side and our fundamental understanding of their underlying principles on the other. Though theory has already identified some first core questions and has provided some preliminary answers to them, it has to run faster in order to bridge the gap and catch up to practice. The existing literature can be toughly partitioned into three clearly distinguishable but also closely interrelated sub-areas: population protocols, powerful dynamic distributed systems, and temporal graphs. The population protocol model proposed by Algoin et al. In 2004 was originally motivated by highly dynamic networks of simple sensor nodes that cannot control their mobility. As the work of Algoin back in 1980, that is generally accepted as a landmark study for distributed computing in static networks. Population protocols could be considered as the starting point of distributing computing in dynamic networks. The other main sub-area originates from the 2005 work of Odell and Wattenhofer, the later work of Kuhn, Lynch, and Oshman, who reconsidered classical distributed tests in a network whose dynamics are captured by a worst-case temporal graph. In parallel, starting from the study of Berman and Kemp et al., an increasing number of groups are interested in investigating the structure and algorithmic properties of temporal graphs with the aim at developing a temporary extension of graph theory. Now, let's look deeper into each one of these lines of research.
Can such a soup of automata really compute anything useful? according to Angelon. Actually, they can compute, but not that much comparing to modern computing system. It is a soup of automata because it is a population of nano-devices interaction randomly with well-mixed solution. Each device tries to reach the stability with a small memory and no control. Most difficult challenge in dynamic network is related to unpredictability, which is different in static network because we cannot predict what will happen next and no feedback acknowledgement. Also difficult to know how much time waiting to receive and send the information through the network because it is changeable. So the problems faced in this theory is the sequential computation, unpredictability, and unguaranteed of the data influence through the network. Static and dynamic network. In a static network, for example, if we broadcast a message, we will know it will reach every distance in the network and it will have feedback acknowledgement. But in the dynamic network, we have to know how it is changes and the maximum upper bound and the time taken to get a message back. That lead us to important thing, connectivity assumption. Network always connected or it has influence over the time with connected. Still need additional knowledge about dynamic network because by knowing the network behavior and making good assumption with a probabilistic assumption, we can classify the dynamic. What are they dynamic, periodic, what the worst case. Network construction. Several natural processing, they can be viewed as an abstraction of fast mixing system. Use population protocol as a model of algorithmic distributed network construction and as potential model for programmable matter able to self-organize in dynamic environment. As a result, network constructors can construct as complex stable networks. Draw a random network and simulate on the distributed memory. The devices can additionally establish bounds with each other, like a molecular bounding mechanism. The idea is to program the nodes to organize themselves into a network that can serve as a memory of size big O of n square. The population draws a random network and simulates on the distributed memory a Turing machine that decides whether the network belongs to the target's one. If yes, the population stabilizes to it. Otherwise, the random experiment and this stimulation are repeated. The more memory we add for each node, the more we can compute and it becomes as a whole as powerful as a Turing machine. Causal influence. The important nutrition with dynamic network is the causal influence which highly affect in space and time. Once information reaches to all points in the network, you begin to be able to draw a conclusion, such as the size of the system, and select a leader. For example, you have some information and you want to tell this information to a sibling that may tell other friends tomorrow, who may tell them a week from now. This information will reach everyone through the time. Once reached, you can process the step.
Then dynamic distributed systems. In 2005, one of the first formal models developed by Aldous and Wharton Floor. Their model is a generalization of classical networked message passing distributed systems. Instead of the static graph, the underlying network is now represented by an unknown and adversarially controlled temporal graph. The nodes are Turing machines with onboarded taps that communicate with other nodes by interchanging message over a wireless medium. It can be used in all possible dynamic work typologies and not just for some special cases. They defined their model in terms of asynchronous communication and studied the token dissemination and routing problems. In 2010, Kuhn, Lawson, and Osma proposed a serious version of model above, which substantially simplifies thinking and treating dynamic networks formally. The nodes operate now in log steps, similarized in discrete nodes either by having access to a global clock or by keeping local clocks similarized. In every round, an adversarial structure selects a set of edges between the nodes, and every node may communicate with its current neighbors. As selected by the adversarial, usually by broadcasting a single message to be delivered to all its neighbors. In this model, all nodes must broadcast in every round all information that they know, which is not a desired property as it results in transmitting very large message that is of size O n times log n. They also developed an alternative approach that used only log n bits per message. The nodes have a guess k of the size of the system and then try to verify whether their guess was a correct upper bound on n. If it was, then it is possible for the nodes to terminate knowing the extra value of n, otherwise they double k and repeat. However, the model still can be improved. Continual connectivity was one of the first assumptions of these models to be questioned. It was replaced by more general conditions of temporal connectivity, that is, connectivity satisfied over time. In participate, the network dynamic may not always be totally unpredictable or greatly. In practice, the network dynamic may not always be totally unpredictable or irregular. The dynamic patterns of many real-world systems, such as human interactions and transportation units, temporal graphs. The main message from exciting research on temporal graphs is that many graph properties and problems become radically different and usually substantially more difficult when an extra time dimension is added to them. The algorithmic problems of temporal graphs can be divided into main types. Online algorithms have no knowledge about the future, where offline algorithms know the full evolution of the graph in the advance. An example of an online class problem on temporal graph is k-token dissemination, which asks to disseminate all nodes as fast as possible. K-tokens that are entirely assigned to some of the nodes. Even so, offline centralized algorithms do not suffer from the unpredictability that characterizes network problems. Still, offline temporal versions of standard graph problems can be substantially more difficult to be solved. Do we really know how to compute in highly dynamic environments, how to represent and measure their core properties, or even how to effectively solve certain computational problems certain time? We are on the road to unfind series of dynamic networks, but not there here. First, is there general rules underlying the complex increase of a network problem when that problem is extended in time? Moreover, most natural applications require an algorithm to operate a dynamic world without knowing or being able to predict and future evolution of the network. Second, there is theoretically a different model for each setting, and usually site modifications of a model results in total different formal properties. This multiplicate is expected to be even more intense in dynamic worlds due to the almost inaccessible variety of different dynamic patterns. Therefore, if possible, Amplification of models of distributed computing is dynamic works would be more than valuable. Finally, we should seriously take into account recent advances in learning and statistical learning in particular as a rich source of powerful methods for the system to learn and thus be able to predict to some extent pattern and of the dynamic works and to adapt its algorithm in order to cope with the new conditions more effectively. That's all. Thank you for listening.